A triple is three numbers that basically satisfy Pythagoras' theorem. So in this case, with 3, 4, 5, that is a triple because 3 squared plus 4 squared equals 5 squared. And in the triangle that this represents, A is the angle in the triple. And it's always between the base, 3, and the hypotenuse, 5. So the geometric representation of this A345 is given here in this diagram. The first number is always the base, the second number is always the height, and the third is the hypotenuse. And these quadrant angles as well, you remember, for 0 degrees there's a triple for it, 1, 0, 1, 90 degrees, 0, 1, 1, and so on, for 180 and 270. Triple addition is defined like this. So if you've got a triple, 4, 3, 5, and another triple, 12, 5, 13, adding effectively adds the angles. So this shows the addition of those two triples by putting the second one on the hypotenuse of the first one. And then the sum of those triples, when you add them up, will be a triple which has got A plus B as its angle. And there's the triple there, with A plus B as its angle. So the question was, how do we find the triple for A plus B from the triples for A and B? And the answer was, we apply the vertically and crosswise formula. We multiply vertically in the first two columns and subtract to get the first element of the answer. So 4 times 12 minus 3 times 5. So that's 48, take away 15, which is 33. And to get the middle element, we cross multiply and add, starting here. So we have 3 times 12 plus 4 times 5. So that's 36 and 20, which is 56. And for the third element, we simply multiply vertically on the right here. 5 times 13 is 65. So that triple will contain an angle equal to the angles A plus B. In the earlier lesson, we also saw an application of triple addition in rotating points. So for example, if we were asked to rotate the point 5, 2 anti-clockwise about the origin through the angle contained in the triple 4, 3, 5. So this diagram shows the setup. The point P52 is here, and they're the coordinates 5, 2. And this triple here, this triangle, is the 4, 3, 5 triangle, which sits on the hypotenuse of the point triple. And what we're trying to do, of course, is to rotate P around through that angle to the point P dashed. We want the coordinates of P dashed. So the way to do it was simply to write down the point triple, write down the rotation triple, and add them up to get a triple for this line here. So we would have 5, 2, and then the third element, which is found from Pythagoras' theorem, 25 and 4 is 29. And then the rotation triple is 4, 3, 5. We added those. So we have 20 minus 6 is 14. And 8 plus 15 is 23. And then here we have 5 root 29. Now because we know OP is root 29 and OP dashed must have the same length, we know that we've got to divide this triple through by 5 in order to get OP dashed equal to root 29. And as I said before, we always divide these numbers by the third element of the rotation triple. We don't have to work out this root 29 at all. So we simply divide these two numbers by 5 to get the answer. P dashed is 2.8, 4.6. Now let's move on to triple subtraction. Suppose we've got a triple, A435, and another triple, B, 12, 5, 13, and we want to subtract them. In the case of addition, of course, we were adding the angles, so here we expect to subtract the angles, like this. Here's the same two triangles, given the same vertex, so that we're after the difference of the angles, which is this angle here. So here's A 435, B 12513, and we want A minus B. Well, you'll remember the pattern for adding triples, and this is the same pattern. The only difference is that the signs are different. The signs are opposite. So we multiply vertically in the first two columns and add. We have 4 times 12 plus 3 times 5. 4 times 12 plus 3 times 5, which is 48, plus 15, which is 63. So the first element is 63. For the second element, well, for the first element we actually started here. For the second element we start here. So we're going to cross multiply and subtract. That's 3 times 12 minus 4 times 5. 3 times 12 minus 4 times 5, which is 36 minus 20, which is 16. So the middle element is 16. And then as before, we multiply vertically on the right. 5 times 13 is 65. So don't be confused by the signs. Here, when we're subtracting, we add here, we add to get 63, and we subtract to get 16. For addition, it's the other way. Addition here means subtraction for this element and addition for this element. So the signs alternate. Now let's see an application of that in finding the angle between two lines. Suppose we have the problem of finding the angle between these two lines. Here's the setup. These are the two lines. This will be y equals x plus 10, and this one is the other one, the first one. So what we want is a triple for the angle between those two lines, a triple that would fit in there. Well, in fact, it doesn't matter whether these lines intersect here or at the origin. We could, if we simply take away these absolute terms at the end, the minus 12 and the plus 10, the lines won't change in their orientation, in their angle. They would simply go to the origin, and finding the angle between these two lines is exactly the same as finding the angle between these two lines. In other words, we can just ignore the elements on the end, the minus 12 and the plus 10, and think about the lines 3y equals 4x and y equals x. So here, this is y equals x. This is 3y equals 4x. Well, from the coefficients of y and x here, I can write down a sort of gradient triple. 3, 4, and then the other number. So this green line here shows the triple. 3, 4, 3, 4, 5 in fact, would fit in there. And similarly for y equals x, we could say the triple, the gradient triple for that is going to be 1, 1, because the gradient of that line is 1. So here's the triple, 1, 1, whatever. Now, because I want the angle between them, I'm going to be subtracting those triples, and that'll give me a triple for the angle in between. So let's see. Well, from those numbers, we can get the first two elements of the triple we're looking for, and that will be enough to define the triple. But let's just put in the third elements here. Obviously, the third element here is 5, and we know we can work that out. And the third element here is the square root of 2, because 1 squared plus 1 squared is 2. And we're going to subtract, so we multiply vertically in the first two columns and add. 3 times 1 is 3, 4 times 1 is 4, 3 and 4 is 7. For the next element, we start here and cross multiply and subtract. So we have 4 take away 3. 4 times 1 is 4, 3 times 1 is 3, 4 take away 3 is 1. And then multiplying vertically here, we have 5 root 2. So a triple of that shape would fit exactly in that space. And there's the angle between the two lines given in triple form. There are ways of finding the angle in a given triple or a triple with a given angle in it, but we won't go into that here. So here's another application of triples in finding the distance of a point from a line. Let's take this example. Find the distance of the point P52 from the line 4y equals 3x. So here we are. This is the point P52, and this is the line 4y equals 3x. And we're asked to find the distance of that point from that line, which is the perpendicular distance, or shortest distance, which will be the length of that line there. Let's join P to the origin, and let's also drop a perpendicular from P onto the x-axis. Now we know we can get a triple for the line. So this line here shows the triangle, or triple for the line, showing the slope of the line, which will be 4, 3, 5 in fact. Remember, we take the coefficients of y and x, so that's a 4, 3, 5 triangle. We can take the triple for the point, which is going to be 5, 2, and square root of 29. And we can subtract those, because if we subtract them, what we'll get is a triple for the angle here, which is the difference between those two triples I mentioned. So the difference between the line triple and the point triple is this angle here. And then all we need to do is to think about making that triple the right size so that it fits in this triangle, and then the opposite element, the second element of the triple, will be the distance we're looking for. So that's the plan. Let's have a look. We start with the line triple, which is the steeper line, steeper gradient, and that's going to be 4, 3, and the third element is 5. We take the point triple, which is 5, 2, root 29, and by subtracting them, we get a triple for the angle, which is the difference of those two angles. So let's see. We multiply vertically and add, so we have 20 and 6 is 26. We multiply crosswise and subtract, so we have 15, take away 8, which is 7. And vertically here we have 5 root 29. So that's the triple we're looking for. Now just think about this for a moment. It's got 26 for the first element and 7 for the second, so it's quite a narrow triangle. If that's 26 there, that would be 7. The triangle will look something like this. And the angle in there is the angle we're looking for. But we don't know if that triangle will fit exactly in the triangle here. It may be too small or too big. In fact, it's too big because its hypotenuse is 5 root 29, and the hypotenuse of this triangle here is the length of OP, which is root 29. In other words, we've got to divide this triple here through by 5 in order to get root 29 there. If we divide it through by 5, we get 5.2, 1.4, root 29. So we've got the right hypotenuse, and therefore that triangle must exactly fit in that triangle there. And in fact, all we want is the height of the triangle, which is given by the middle element there. So the answer is actually 1.4. That distance is 1.4. Now, if you were to look carefully at this, you'd see that we've done a lot of superfluous work. We didn't need to work out the root 29. We didn't even need to work out the first column at all. All we needed was that 7, which we could then divide by 5. So we could have just done it like this. We don't need to do the first one, so we go straight to the middle element. 15 take away 8 is 7. And then dividing that by 5, which is the third element of the line triple, we get the answer 1.4. So this is the entire working out here. Well, to finish off, let's just compare the Vedic method you've just seen with the conventional methods. Now, so far you have seen 3 Vedic methods. You've seen the method of rotating a point by a given triple using vertically and crosswise to add up the triples. And this is the conventional formula for rotating through an angle A. You're given your point PQ, you multiply it by this matrix, by the angle A, you have to work out the cosine of A, the sine of A, and so on, and then you have to multiply out and you get P dashed and Q dashed. Now you remember how easy it was to do the rotations using the Vedic method and vertically and crosswise. This is the formula for finding the angle between two lines. If the lines are y equals m1x and y equals m2x, where m1 and m2 are the gradients, this is the formula. So you have to take those values of m1 and m2, work all this out, dividing by 1 plus m1 plus 1 plus m1 m2, and then find the inverse tangent of that to get the answer. Calculator is absolutely essential. For finding the distance of a point from a line that we just did, if the point is hk and the line is this, ax plus by plus c equals 0, this is the formula for working out the distance. You see it's pretty complicated. You have to work out the top there. The vertical lines means the absolute or positive value. And then you have to work out a squared plus b squared square rooted and divide the top by the bottom. A lot of work. But what we've seen here is the Vedic formula, the triple method, gives you the answer using one formula, just the triple addition and subtraction method. One pattern, one formula will do all of these. Just compare these different formulas, how different they are, and how difficult it is to work with them. So here are some other applications of triples. I'll be going quite fast, so you might want to be prepared to pause. So finding sides of right-angled triangles using vertically and crosswise, or finding angles using the triples. All of these things, some of them we've covered already, but triple geometry is a topic, and special angles like this, half angle, all covered. The sort of question you might get in an examination, given sine A and cos B to find these other functions. All of these things are easily done using this triple method. Proofs we can do too, things like this, inverse functions, proofs of all kinds, and solving equations like this. And this is a special kind of trigonometric equation which is quite popular in exams, which you can solve very easily using the triple method and vertically and crosswise. Transformations, we can do these rotations, you've seen this. We can do reflections as well, and even rotating curves like this, y equals x squared. Complex numbers, triple addition is the same as multiplying complex numbers, and triple subtraction is like dividing. And we can do square roots too and write the answer straight down using the half angle triple. Conics, this triple here actually represents an ellipse. We can do hyperbolas and parabolas and offset circles like that. And also arbitrary equations which satisfy Pythagoras, they have the triple method applied to them too. Simple harmonic motion, these three triples here represent distance, velocity and acceleration, and problems with simple harmonic motion become just finding numbers in this 3x3 array. So we can solve problems like this. Projectiles too, there are three triples, and acceleration, velocity and distance triples, which can be combined into a neat pattern like that. Forces in equilibrium, we can solve forces using triples and other problems, and work and moment of a force as well. And we can go into 3 dimensions and have a 3-dimensional triple, which is called a quadruple, and have applications in astronomy and so on. And this is just the proof of triple addition for anyone who's interested.